we had 2 courses assigned for this this time around. There is a third if you find you really like the visualization material or you think you might need really clever visualizations. I would recommend that you do the part 3 of ggplot2. You don't have to do it for in here, but it does contain some useful information. If you want to really go into this full-blown kind of data science-y kind of area. So we're not going to go that far, though. We're really stopping with what will be useful in terms of creating scientific visualizations, the type that you could put in papers. So that's really where we're going to focus. Also a reminder that we flipped the schedule slightly. Last time, or for this week, we were supposed to do ANOVA, but we flipped it with data visualizations. So next week will be ANOVA. And the reason for that is because I realized that a lot of the diagnostic and other types of plots that you typically use in ANOVA and regression, you would already need to know ggplot2 in order to create them. So we flipped the whole schedule around, so we did data visualization first. So this really forms the foundation of a lot of both exploratory and descriptive and inferential types of plots that you might create for a variety of procedures and analyses. So we'll step through it. It's a very general purpose framework, ggplot2. So you can do a lot with it. So yeah, today I'm gonna give you first a real brief reminder about software updates because we haven't talked about that really in much detail before. 2, I'm gonna go through a walkthrough of ggplot2. That really means kind of a big picture view of what ggplot2 is and why we use it. I'm going to point you at a new cheat sheet, which is super useful for when you're working with ggplot2 and you don't remember the names of the 50 or 60 things that you need to occasionally reference. Then walk through all the major aspects of ggplot2. And you went through all of these in the data camp lessons, but you didn't necessarily spell them out quite this way because you kind of follow along the river of exercises, right? But the kind of 6 things that you need to pull away from those lessons are what geometric objects, geoms, aesthetics, statistics, coordinates, facets, and themes, all of which alter different aspects of visualizations. So we'll cover each of those in turn. So as first, brief reminder. We've been using R for a while now. As we use R more, as we use R longer, new versions of R will be released. It is very important that you install those new versions of R as they come out. The reason for that is because even in the last project, some of you were using references that are no longer supported in TidyVerse. For example, if you'd used the name of a data frame $ variable name inside a TidyVerse function, that is no longer supported in dplyr. That should have never been supported because that totally breaks out of the dplyr philosophy. But now it just doesn't work at all. So if you try that, it will break. And that happened when I tried to run your code, so I actually had to modify a lot of folks' code in order to get them to run on the new version of TidyVerse. So what that means is you really need to be operating on a new version of R and of all the packages. R is pretty easy. Just go to the R website and download it again. And please do that today. Actually choose to do that today before you work on your project. After you're installing R, one of the things that happens is that will break compatibility with certain aspects of RStudio, so you also have to download a new version of RStudio. After you do that, then inside RStudio you use this command, update.packages, parentheses, ask equals F, which of course means false. What ask does is it doesn't ask you to approve each individual update. So if you leave that out, it will ask you for all of them. So if you have 50 packages that need updating, it will say, do you want to update this one? Yes, no. And you hit yes. Do you want to update this one? Yes, no. Yes. And you just do them all over and over again. If you do ask equals false, then it will just do them all automatically. So it will update everything in one big swoop. Sometimes when you do this, packages will disappear because the old version and the new version will be totally incompatible for whatever reason, in which case you might need to reinstall packages from scratch. So please do this, and in fact, anytime that you see a warning that says this is not supported in R version whatever, or this was built in R version whatever, those things mean that your version is now out of date, so you need to update. In most cases, again, this doesn't change a lot, but it can make important little changes, and dplyr is one of those where that can happen. As I mentioned in a couple weeks ago, the TidyVerse is updated frequently. It is an actively developed system. So it does change pretty often. And if you want to use the newest TidyVerse functions, you have to have the newest version of R. So that's why it's important. So that's just a brief reminder of doing all of that. So yes, please update R, please update RStudio, and please update all of your packages so that they are in current version. If you want to check, by the way, you can type version to get the current version of everything that you're looking at. We'll notice that right now we are in short summer because every version of R has a name. This is R version 3.4.2. If you are not running 3.4.2, you need to update. Okay? And I just did that using the command version. No parentheses. Okay. And that was released at the end of September. So if you haven't updated in the last 2 weeks, you need to update. Okay. So visualization, what we're talking about today. Visualization is arguably the most important aspect of data analysis. Anything that you do, statistically speaking, in social sciences relies on assumptions, and in many cases there are far more assumptions than we actually have necessarily time to go check out, statistically speaking. A lot of times you would just say, I'm sure everything's normal, and kind of move on. In SPSS, the main reason that you do that is because normality is really hard to assess. You have to, even if you look at normality statistics, if you look at skew statistics, kurtosis, that doesn't actually fully capture normality issues because you can have bimodal distributions and all kinds of other issues going on. So visualization becomes the way that you assess assumption checks in a lot of cases. SPSS makes this really hard because the only way to do histograms is to go through either the legacy dialogues or go through that weird chart builder thing, and it takes a lot of time, so if you have like 50 variables, you're much more likely to just skip the whole thing. In R, this is a lot easier. I'll actually talk about a really easy way to do this that's kind of based on the ggplot2 system. It's something that you didn't cover in DataCamp, but you will need for the project this week. But in general, this kind of idea of I need to look at my data, it should really be the first step in basically every analysis you ever do. So arguably most important, that's you, but it's also people on your project. Data visualization allows you to quickly communicate key findings to other people working with you. It also does the same for stakeholders. If you haven't been out in industry yet, you probably are not super familiar with that term, but stakeholders are people who need to make decisions on the basis of what you're telling them. So it is important that your analyses and your output are understandable and communicable, something that is easily interpreted by the people that you're trying to give it to. So that means if your stakeholders are other people in your analytic unit, like if you're in a consulting unit or if you're in a human factors unit or whatever it is, that's very different than if you're going to be talking to C-suite folks, like CEOs, that kind of thing. So visualization is the way to bridge a lot of those gaps. ggplot2, like the rest of TidyVerse, tries to guess what you're doing. And that's a real advantage of ggplot2. And TidyVerse in general. It can be a little confusing sometimes because it will do things that you don't expect. But in general, it tries to guess what you're trying to do and then glosses over the details. Notice that we are not really talking about base R graphing much. We used like hist, we used boxplot, we used a couple of those like base R graphing functions. But we're not really talking about how to make pretty graphs with R. We're not talking about how to do multi-layer, multifaceted graphs with R. We're sticking to ggplot2, and the reason is because base R graphing is horrible. It is just a nightmare to work with. It is very complex needlessly, and ggplot2 skips over a lot of the nonsense so that you don't have to deal with it. A good example of that is we've actually dealt with already when trying to put together bar plots or bar charts. If you remember from a couple projects, I asked you to mysteriously use the table command in order to create a bar plot. And the reason for that is because if you just tell R to do a bar plot, it literally takes the numbers you gave it and makes them into bars. So if you have a 50 case data set and you say bar plot variable, it will show you 50 bars of all those values. So instead you have to tabulate, you have to create a frequency distribution of your own data set and then feed that into bar plot. So that's the kind of under the hood stuff that ggplot does for you. You can do it that way. You can manually go in and say, I'm going to force this to use each individual number in this data set. That's the identity that was talked about in DataCamp. But by default, it won't do that. If you give it an x and a y, it'll look at the data type of x, the data type of y, and guess what you're trying to do. So that's a real flexibility that's useful here. The syntax allows you to try out a lot of different visualizations really quickly, which is extremely important, especially when trying to create things, for example, for publication, where you're not exactly sure where everything's going to get placed. The version of this that you probably do now is pixel perfect moving with the arrow keys in Excel, trying to nudge over lines and nonsense. You don't do any of that anymore. This gets around it by programmatically specifying everything that you need. The other real advantage to it is the data pipeline. Remember that when we create R scripts, the goal is for line 1 to essentially start a blank slate, and then for the end of the program to have all of the output from your entire analytic process done. That means that you put ggplot at the end of McGritter pipes or on their own. And what that allows you to do is fully process a data set completely from scratch and create figures every single time. So what that means is if you discover, oh, wait a minute, 60 lines of code up, I forgot to do reverse coding, I missed a mutate command, you can just change that one command and hit run all, and it'll regenerate everything you've already done, including figures. So that's the real advantage of including ggplot in the McGritter kind of path and using full data pipes, the full data pipeline in order to get from raw data to visualizations automatically, fully in between. Okay. So what specifically does it get us, again, under the hood? Mathematics, you don't have to do. I do have you the example of bar plot already. I'll actually show you an example of it real quick. If we look at the MT cars data set, which is a built-in data set in R, you automatically have access to MT cars. If I just say I want a bar plot of MT cars, MPG, then that basically right there has taken all of those numbers and turned it into this. So if I use it on a factor variable, it'll do the same thing, like we do sil. Like that makes no sense as a bar plot for this sil variable, which is very clearly a factor-oriented variable. So this is what bar plot does by default. So normally we would table it, and I show you what the table command does, is it basically creates that frequency distribution, and then you feed that into bar plot to get what you want. So we avoid all of those little steps by using ggplot, instead just creating a basic aesthetic and then putting the variables we want into it. Actually, we can go ahead and create a ggplot too. A ggplot of MT cars, and we're creating an aesthetic where x equals, what was it doing, sil? And then we create bar. It's harder than it should have been. And now we get exactly what we were trying to go for in a much nicer format. And I'll show you also the regular plot form so you can contrast if you haven't done that on purpose. There's your default plot, and there's your default bar plot. Similar, you get the same answers, but a lot more steps involved to get there. Okay. So, yeah, much nicer looking. ggplot defaults are a lot easier to get from where you want to, from the default plot to what you need for a paper or what you need for a publication. Much easier to modify. It also gets us to think like data scientists in terms of visualization. You probably noticed this in data camp. There was a lot of emphasis on interpretation of figures meaningfully in terms of interpreting what data sets look like. And in a lot of cases, that's because you're working with populations in traditional data science. Like, you're actually not sampling all the time. You're actually working with literally a population. Like, there's no generalization or inference going on. You're just saying, are there patterns in these data? And that is meaningful to me. It means that they have a whole lot more techniques for looking at data and trying to explore and poke around and understand what's going on that we typically don't do in the social sciences. That gets us in trouble a lot because you will find that there are data sets where analyses have been done inappropriately because no one ever bothered to check what the data look like. They have inappropriate distributional assumptions, or they're just in general not appropriate given the type of data that you're working with. So these things we can get around by doing some clever, quick, and easy to use visualizations. ggplot2 is based on the grammar of graphics. That is a phrase you would have seen quite a lot. Each ggplot has its own aesthetics, which are sort of like master aesthetics that drill down into the subcomponents of the ggplot. Also have geometric objects, geoms, that have their own aesthetics. which is how we create our ggplot statements. So this one right here, as you just saw, I have ggplot. I have empty cars going into it. I could alternatively write it like this. Same thing. Where I'm feeding at the end of the pipe, empty cars becomes the first argument of ggplot. And so then we have ggplot aesthetic with cylinders on the x-axis, and then create a geometric object that is a bar. So you see that that will create the same thing that it created before. So this is kind of your standard form, but important to recognize the pieces. Again, this is an aesthetic right here. This is also a master aesthetic, so it's the highest order aesthetic in the ggplot. You don't necessarily need one. That, for example, does exactly the same thing. Every object, every geometric object in a ggplot has its own aesthetic, and you can modify those aesthetics at will. The advantage to using this higher order aesthetic is then all of the geoms that occur below it inherit its properties. So I could create 5 different geoms right here, and they would all have whatever was in AES. But for this second statement, if I added another geom, it would be referencing nothing. It would have no aesthetic, so you would get an error. So this is the reason that you would use one versus the other. In general, and this occurred early in the data camp material, this is best practice. To create sort of your base model graph in that first line, in that first aesthetic, and then add things you want beyond that. But it allows you to do some really cool things in terms of layering, because you can, for example, create a bar chart, and then I could create a new geom with a just arbitrary distribution here and fit a normal or a uniform or a Poisson or whatever I wanted to do right there, just totally arbitrarily. You can construct these graphs however you want. That's the flexibility that it buys you. So yeah, general best practice, create the ggplot object, specify your data, define its fundamental aesthetics. You can put them in the geoms, you really shouldn't most of the time, but then add geometric objects that you want, which may or may not have their own aesthetics that you define. They do always have aesthetics. That is important. Because here, the aesthetics of this geom bar are x equals sil. It's inherited down. So it does have aesthetics, you're just not specifying them. Use the plus symbol to combine features. This is a real common error when you're first learning ggplot. You try to just go to a new line, or you try to put the plus on the next line, all sorts of weird little ways to do it. You have to end with a plus for multi-line coding, but you don't have to. So I just have this example right here of empty cars. I'm going to copy it back out. This is identical to this. It is not, however, identical to this. Those are different statements. Also a common error. The reason that those are different is because the way that R works is at a line break, it assumes that you mean the next command unless it has reason to believe otherwise. So the way R interprets this is not actually with that indentation, it actually interprets it like that. Because it sees empty cars, run ggplot command. Done. There is no reason for it to finish, so it says statement over, finished. And then it tries to run this next command on its own. So it will not work. That plus at the end of that line communicates that that's a running command. Because it says plus, oh wait a minute, a command can't end with plus. Therefore I have to process the next line too. That's what's happening inside R. But you can put them on the same line, like I did up there. You can also mix and match. So if you wanted to add another plot up here, for example, I could totally add a plus and then add whatever I wanted right there. So just keep in mind how R is processing those lines, because it will really dramatically affect what product you get at the end. Okay. When you call ggplot objects directly, you display them. So it didn't ever really explicitly say this, but that's why you can, for example, assign a ggplot to an object and then either call the object or add more things to it using the plus operator. Because whenever you call that object directly, that's what makes it just appear. If you want to get details of the object, it's a little more complicated, but we don't usually need to do that. Getting data into ggplot2 friendly format, you can do almost anything. Like as long as the numbers themselves are there, there is probably some way to coerce ggplot into creating the graph you want. You might, however, have to use some really complicated statistics layers. You might have to do some inline restructuring and some weird stuff. In general, it's best to, instead of doing that, to take this approach right here. For univariate statistics, isolating your outcome value as a single column, whatever it is, and if your data are longitudinal, restructure so that all DVs are in a single variable. So if, for example, you have a time 1, time 2, time 3, you will have an easier time with ggplot if you gather that and turn those time 1, time 2, times 3 into an identifier variable, like T1s, T2s, T3s, and then a single column of outcomes. It will be much easier to use ggplot in that condition. Isolate all of your grouping variables as unique columns. That also means that if you have conditions, you will probably need to split them up. So if you, for example, have randomly assigned people and have conditions 1, 2, 3, 4, but that really represents a 2 by 2 between subjects or within subjects design, then you're probably going to want to convert that into 2 new factor variables that each have those descriptors. In multivariate, you want to isolate each DV as a column, and you still want to isolate your grouping variables as unique columns. But as soon as you get into multivariate, this gets a little weird. So that's usually when you start doing things like panel-based, like using facet grid, doing like panel-based stuff. But yeah, there's a lot of different potential ways to do it. Always convert to correct types. This is super, super important. ggplot infers a lot about what you're trying to do based on the data type that you've given it. So if you have, for example, in our factor variable over here, or in our empty cars variable over here, or data set, yeah, a lot wrong words. When I look at the rundown here, these are all pre-specified as double, which really means numeric. So because of that, if I fed sil in as an x variable, it would assume it was continuous and treat it as continuous unless I re-specified everything otherwise. And sometimes that'll work, but sometimes it causes a lot of weird visual quirks that you don't expect. So in general, you want to convert this over ahead of time if you can. You can actually see the visual quirk here very manually. The sil has been interpreted. I don't know why that's popping up. Sil has been interpreted as a continuous scale right here. So that's what we end up with in our bar plot with this 3, 4, 5, 6, 7. 2 ways to fix that. One, we could go back in here and actually change it into a factor. That has fixed this plot down here. Alternatively, I could use scale aesthetics in order to, or coordinate aesthetics, sorry, in order to fix it. So I could use scale underscore x underscore discrete as a way to force this back into a discrete form. But as long as you set it up correctly ahead of time, again, it's going to guess better. So always do these kind of data conversions beforehand. Okay. General aesthetics that you might need. There are a lot of aesthetics. The most common ones you might need, X and Y, which are your basic axes definitions, color, fill, size, shape, weight, alpha, line type, and labels. The ones that are a little less intuitive here are shape, which is a marker type. There's actually a whole database of weird little symbols that can be used for shape. It ranges from 0 to like 25-ish, I think. And the last few also take color commands, so you can do things like have a circle filled with a gradient color or whatever you might want to do. Weight actually refers to line thickness, and alpha refers to the alpha channel in color, which is really an index of transparency. So if you want to have dots overlap each other and get darker, then you need the alpha channel. Line types are used for line patterns, dashes, double lines, etc., and labels just refers to text. All different geoms will inherit different aesthetics. So it is important that you determine what geom you want first. Like, don't go in here just saying, I'm just going to guess at what the best visualization is. I literally, to this day, still like sketch out on paper a little like, I kind of want it to look like this, and then make sure it actually looks like that once I create it. Just because it's real easy to head down the wrong path and end up fighting with the code to create something that when you look at it in the end, you're like, wait a minute, that doesn't make any sense anyway. So I like to draw it out. So decide your geoms. Are you using bars? Are you using lines? Are you putting lines on top of bars? Are you putting lines on top of box plots? Like, what are you doing? How many things are there, and how are they organized? And that will help you determine which aesthetics are useful. Within a geom, aesthetics can be defined as attributes instead of aesthetics, which are the same things in terms of these variable names down here. Not so much x and y, but size, shape, weight, etc. But an attribute is applied universally across, and an aesthetic is applied based on values of something else. So you could, for example, say weight equals 0.1. That makes it an attribute. So now everything within that geom will have weight 0.1. Or you could put it within your aesthetic and say weight equals variable name, and then the weight is determined by the variable. That's the only difference. The variable names themselves are identical. What changes is how you're using them. This cheat sheet is a really handy way to figure out which things you need to worry about in the first place. I'm gonna click on it so we get the whole thing. Yes, no viruses. I will warn you before we get too deep into this. This is based on an old version of ggplot2, so not all of this is quite current, but most of it's there. This will give you a breakdown of all the different geoms that you can use and what kind of situations you would use them in. We have, for example, one variable continuous, one variable discrete, continuous x, continuous y, discrete x, discrete y, or continuous y, discrete x, discrete y, and so on. The real advantage, however, to this is it tells you which specific aesthetics it takes. So like here, if you said, oh, you know what, I really want to have a jitter plot, well, the things you can do with a jitter plot are specify x, y, alpha, color, fill, shape, and size. So this cheat sheet becomes a really useful way to figure out, well, what exactly do I put here? And that gets especially important in some weird cases. So for example, places like geom bar, you might think, oh, I'm talking about height, so I should probably have a y element, but no, it only takes an x. Down here on error bars and crossbars, you might, and line ranges, you might think, oh, I can just feed my x variable in and make an x bar. But you'll look and you say, oh, wait a minute, it needs an x, a y min, and a y max. Those are just things I don't even have. So this communicates to you very quickly that your basic aesthetics won't work with these. You'll have to do something else. So this is where this is useful, and I would recommend that you refer to it a lot. There are a few things that don't quite work the same way. The biggest of these is going to be labels. XLab and YLab were the old way to specify labels. That's now done inside scale aesthetic, or inside scale coordinate layer. So you do like scale underscore discrete, or scale underscore x underscore discrete, or I forgot what it is. But you do the scale command. Oh, here it is. Yeah, scale underscore x underscore discrete or continuous or whatever. And then in your first element, you give it a string, and that's what sets your labels. You don't do it with XLab or YLab. Those commands won't work anymore. So there are just a few weird little situations like that where this is off. So if you find it's not acting the way you quite expected it to, then that may be what's happening. Okay. Defining specific colors. So color theory is something we're not going to get into a whole lot of detail here about, but you do need to be familiar with it. This is what's most color systems, including ours, are based on computers, are based on what's called web color. Web color is an old way of defining a color on a web page. It is still in use. All web pages are defined this way as well. It's based on a series of 3 hexadecimal numbers. Hexadecimal is a base 16 counting system. It works like this. So we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So if you see an F, it means 15. That in turn means 0, 0 really means 0, 1, 0 means 16, 2, 0 means 3, 2, and FF means 2, 5, 5. The reason hexadecimal is in use is because FF is actually conveniently the size of a byte. It is 8 bits of information. The full triplet here is the size of a byte. FF, FF, FF. You're going to get 3 bytes of information. So Windows has a super helpful calculator. If you find that you need to get a specific color, then you may need to use this calculator. And there should be a Mac equivalent, although I don't know what it is. You should be able to get the equivalent using the calculator. If I go to Calc, there we are. By default, if you use the calculator in Windows, you will see this, which is your standard calculator. You can see the word standard up there. However, there's also a programmer calculator. The programmer calculator allows you to do mathematics in hex. So this is where you find a lot of value in determining specific colors. Say, for example, that you were interested in, or you needed a 50% gray. Okay? So if that means we need 50% on all 3 channels of color. So that number in decimal would be 128, right? What is 128 in hex? Do you know? I do. But you don't have to do it. Right here, I can click decimal and type 128, and you will see the hexadecimal version appear right above it. So you can see in binary, this is 1 byte. It's got 8 characters in it. In octal, which is base 8 system, it's a 200. In decimal, we have the 128, and in hex, there's an 80. You can do it in reverse. If you click on hex, for example, and I type DE, you will see that the equivalent of DE in decimal is 222. So you don't need to learn hex. You don't need to learn hex conversions. It is not worth your time. But you do need to know how to use this tool. So if I wanted to tell you to use, if I told you, for example, you need a 50% gray, then you would say, well, what's 50% of 256, because that's the maximum value. That value is 128, and then you convert it over to hex from decimal. Okay? Alternatively, I believe I could do FF over 2. Yeah, I get 127. There you go. Same basic idea. In terms of actual color, colors are represented in what are called hex triplets, which is 3 bytes of information. We have a red channel, a green channel, and a blue channel, RGB. There are alternative color concepts. You might, for example, see CMYK is an alternative way to conceptualize color, just cyan, magenta, yellow, and black. But in R, we're going to stick to RGB-based color systems. What this means is you take these numbers as percentages of the byte. So this is really 3 characters, FF0000. This is really FF00FF, not a straight line. And FF means 100%, 00 means none, and then everything in between is a percentage. So that's why we just looked at half, right, as being the equivalent of 128 in hex. So here, for example, I have no red, no green, and no blue. This is an additive color system, so that creates black. That's the absence of color. 0, 0, 0, 0, 0, 0. If I have all the colors, FF, 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 what do you think that creates? White. So that means that anything in between can be created by combinations of colors. So we have FF 0000, that's 100% R, so red. In this case, it's C0, C0, C0. If I go back into my calculator, and I go into hex, and I go C0, you can see that's a decimal 192, and if I divide that by 256, well, 192 divided by 256, 192 divided by 256, you'll see that I end up with 75%. Okay. So, and that is, yep, 75% of the way to white, which means it's 25% gray. Okay? That's why that flips around like that. Okay. And this one down here, FFOOFF, 100% red and blue, is fuchsia. You might think it's purple, but that's because you don't understand color. All right? If you get confused by any of that, if you need specific colors for specific reasons, I recommend this web page, which you can just go find it. If, for example, you need, I want a really light blue, but not too offensive of a blue, maybe that one. You can just poke on it, and then it gives you the hex code right there. 0C-A1C6 in this case. It also gives you the RGB equivalents in decimal so that you can see kind of what's going on. You can see this color has a lot of blue in it, a little bit less green in it, and very little red. Okay? So these tools together allow you to pick any random color you might want. So keep that in mind. Okay. Colors can also be referred to by name. There are a number of built-in color names in R. I think you used black and red. You can just put them inside a string, so you can do that. But those colors are pretty loud, for lack of another word. Most of the defaults are going to be the brightest possible version of those things. So if you just say red, you're going to get this red, and that red is very red. That is an extremely red red. So for particular purposes, you might not want to have something like that, in which case you might change it. All right, so those are the basic aesthetics. We also have scale aesthetics, which is a little different. The default use of scale aesthetics is to take one of these starter points and then continue it with continuous, discrete, date time, log 10 time, or square root. You only talked, I think, about continuous and discrete in DataCamp. But if you're trying, for example, to create a scale of dates, then you would not do that. You would want to use date or date time. And similarly, if you're using logarithmic scales, you would change that as well. All of these are followed, so you could have scale underscore x underscore date time. You could have scale underscore color underscore log 10. You can mix and match them however you want. In certain cases that won't quite work because you'll have, you won't be able, for example, to do fill. Well, you could do fill with discrete. Yeah. There's some combinations that might not work there. So just, again, this is where the sketch is handy. If you have a sketch, you already should kind of vaguely know what you're trying to go for. This is real important when you're dealing with legends. It will be your intuition, if something is wrong with the legend, to try to fix it with a legend command. That's probably not right. If you need to change the title of a legend, you actually need to change the title of the scale that the legend contains. Just a hint. Okay. For scale modifiers, you also have all take vectors. These are limits, breaks, and expand. What those all allow you to do is essentially cut off a scale on the outside, include individual points in a scale, or pull the scale apart. You usually don't want to use these. These are not really a great idea most of the time. There was an extensive discussion, I think, in Data Camp about why you shouldn't do that. The short version of that is that doing this actually makes data disappear, literally, from your data set. So it just stops processing them at all. That means that if you, for example, want to zoom in on a part of your data set but keep a regression line or other summary statistics intact, if you use these commands, it will literally pull those data away, and the part that you look at won't contain those data anymore. So if you had a range of 1 to 5 and you had like 1 or 2 outlying cases at 1 and 5, and most of your cases are between 2 and 4, you might intuitively think, oh, I'll just draw limits at 2 and 4. But if you had a regression line on that graph, then those data points would not be used in the calculation of the regression line. So you generally don't want these. This is a very specific situation that you would use these. Most of the time you want to use the coordinates layer instead, which is what allows you to kind of move around what you're looking at rather than actually modifying the data. Other useful aesthetics, jitter is useful for exploratory plots. You should almost never use jitter in a published paper. I would really not recommend it, because jitter actually, all jitter does is it adds noise to the location of a point. So in visualization, that's useful for all the reasons that were covered in Data Camp. The idea that that if you have a huge pile of data, it can be very difficult to tell where the data actually are. The traditional way to deal with that in social science is choose a different graph. Like, that's the advice. Like, if you had a scatter plot and you only had 2 Likert type scales on top of each other, that means there's only 5 by 5 possible points. So you end up with just this weird looking mash of points. And so the traditional logic in that would be, oh, well, don't do that. Don't use that graph. What jitter allows you to do is it actually allows you to see that relationship anyway. But again, it literally adds random noise, like essentially unsystematic error to your graph. So don't use it for published stuff, but it is useful for diagnosing and for exploratory work. Position is real useful when you're repositioning data. The most common place you'll use position is in terms of bar plots. When you want to do stacked plots or side-by-side plots or just otherwise reorganize where the bars are, you'll probably want to use position. You can also use position in cases like positioning of the legend. Legend might be positioned above, below, around, or arbitrarily somewhere on the screen. So you might use it for that too. Those are probably the 2 more common situations. In terms of aesthetics, in terms of reusing aesthetics for your own projects, do not do this. Here I have ggplot, AES, var1, var2, and then I have a point with a color specified, a size specified, and a shape specified. Just as a reminder, these are aesthetics, these are attributes, because these attributes are universal for all geom points. These are aesthetics because these get trickled down into different versions of geom points. Okay? I'll reiterate this one more time. The reason that we have this kind of organization is because things get inherited down. So this geom point actually has an aesthetic called x equals var1, y equals var2. You just can't see it because it's inherited from the higher order plot. These attributes then get applied universally to all geom points. So every point will have this color, every point will have this size, and every point will have this shape, but every point will have a different x and y depending on the values of var1 and var2. That's what that statement implies. So here you can see, though, that I've given the same attributes to all 4 of these geom points. Do not do that. You can instead redefine your own variable, doesn't matter what it's called, as your geom point, and then add that to each of your ggplots. This is still not the optimal way to do that. What you would really want to do is use gather to gather all of these variables and create a column called var1, var2, var3, var4. And then you would use a single ggplot with a command with a facet grid on the end. That's like the ideal way to do this. But quick and dirty, this is not bad. And for your own code, especially in a situation where you don't necessarily need them to all be side by side, then this works totally fine. Okay. Statistics. Statistics peeks a little bit under the hood of ggplot2. There's a lot of statistics that are done for you. Again, remember that there's ggplot will guess as to what you want in a lot of cases. Geom smooth is a really good example of that, where geom smooth will automatically calculate predicted values for some kind of line. That might be a lowest line, the smooth curve. It might be a linear regression line, whatever it might be that you specify. But it's actually working through the statistics layer. So the statistics layer, you don't usually need it in most cases for most social science stuff that we do. The kind of things that we work on usually will be handled totally fine with the existing layers. But there are certain situations, like if you want to add error bars to plots, if you want to add like an overlaying normal curve, those kind of things where you might need to dig into this layer. There are two ways to do it. One, you can calculate the statistic yourself as a new variable and plot it. There is nothing to stop you, for example, from creating a linear regression equation on your data set, creating a new variable that is the predicted values based on that equation for each case in your data set, and then just plotting it. You can do that. That's totally fine. If that makes more intuitive sense to you, you probably should do that. But you don't have to. You can instead add a stat layer using StatSummary to actually give those predicted values of y given x. So you can do it either way. And again, ggplot is super flexible. You can convert whatever you want into whatever you want it to look like. But StatSummary is the more quote-unquote correct way to do it. It is definitely the more tidy way to do it, because predicted values are not actually in a data set. So you wouldn't, in the TidyVerse philosophy, you wouldn't do that. So yeah, StatSummary is used for summarizing any y data given x, stat function for predicting y from x, and StatQQ is used for QQ plots, although you're probably not going to make too many QQ plots. So here is a StatSummary call that came directly from DataCamp. And I felt like in DataCamp it went through this real quick and did not actually explain what this was and how it worked. So we're going to step through it. This command creates means on, well, actually, let's just run it. See, seeing it will help. Iris, of course, is another data set that's built into R. So you always have access to Iris. There we go. This creates mean plots with error bars. Okay? So how does it do that? So again, StatSummary summarizes an observed y given a particular x value. So in this case, we have 3 x values, and we're trying to create summary statistics of those 3 x's. So StatSummary makes more sense here. If I were doing something else, I might want stat function. So in this case, we have an aesthetic set to x of species and y of sepal length. So that will give our base aesthetics. So that's straightforward. We don't need to worry too much about that. Then we have this StatSummary command. StatSummary is run on fun.y and geom. So what StatSummary does is it runs some other function outside of, not necessarily outside, but some function that's not part of core ggplot2. It runs that function and then applies a geom to it. In this case, it's a mean. So this is literally the base R mean function. And what this says is use the mean function in R and calculate that on Y given each X. Then create a geom point for all the values. That creates 3 values because there are 3 values of X in this data set. Okay? So this first one I hope makes more sense. All it's doing, fun.y means for y, run this function and create this geom. Okay? The second one's a little weirder. This is StatSummary, fun.data, fun.args, geom, and width. The pieces that are more logical about that are geom, so clearly you want an error bar, and width, which is a 0.1. So let's first jump over here and look at error bar. And you'll see that error bar takes an x, y max, and y min. That's a little weird. We haven't dealt with those before. Could I literally specify y min equals and x min and y max equals, I'm on the wrong line, here we go. Y max equals and y min equals in my aesthetic. Could I do that? I could, but it wouldn't be a summary number. It would be from my data set. So again, I could literally create x mins or y mins and y maxes for every variable in my data set and then feed them in as an aesthetic. But that's a real weird thing to do because, again, those data don't actually exist. So instead, we're going to run it through another function. This function is contained within the, this function's a little weird. What you're seeing right here is mean underscore SDL. That function is a wrapper. It does not itself do anything. It calls this function, smean.sdl, and then it reformats those data. So let's see what they all do. I go back in here and I get a library hmisc, and then I calculate an smean SDL, can't type, SDL on mtcars, we'll do mtg. It returns a mean, a lower, not sure what that is yet, and an upper. Not sure what that is yet either. So, if we go into the help file for smean.sdl, coming from hmisc, you will see it right here. Smean SDL takes an x, a mult, which is by default 2, and uses na.rm equals true. So if I look down here to try to figure out what that all means, x is just a numeric vector, great. Mult is the multiplier of the standard error of the mean to use in determining confidence limits. So that means that is plus or minus 2 standard errors by default. That is a weird number for us. We would normally use plus or minus 1.96 standard errors for a confidence interval, or plus or minus 1 standard error for a regular sort of standard error limit. So we probably don't want mult equals 2. We probably want mult equals something else. In this case, you can see the argument then gets passed to it called mult equals 1. That's where we're overriding the default parameter given to mean underscore SDL. But wait a minute. This is still mean underscore SDL. What's the difference between smean.sdl and mean underscore SDL? Aha! Same numbers, different names. That is all it does. The only function of mean underscore SDL is to change these 3 labels into these 3 labels. And the reason it does that is because those are the 3 labels that error bar takes. That's it. That's the whole path we had to take in order to get back to having an x, a y max, and a y min we want. Everybody see that? That full path. So the important things to notice here, though, is that arguments takes a list, specifically. So that's why it's encased in list. For fun.data, we have mean underscore SDL, and we're past mult 1, so I bet you can guess what would happen if I pass mult equals 1. Now I only get it plus or minus 1. Okay. If you want to do confidence interval, you could do it as 1.96, same thing. And that's a 95% confidence interval, of course. You would have to change it for something else. If you wanted a 90%, easy enough. Okay? I change that to a 1.645. There we go. Okay? So once we have these numbers, that becomes what gets graphed in the statement. So, yeah. So we're passing mean underscore DL, SDL. By default, it's going to pass y, given x, because that's what summary does. Fun.rs tells it to use a mult of 1, so that's plus or minus 1 standard error. It's going to use the error bar geom, and it's going to use a width of 0.01 as an attribute. So everything will have width of 0.1. And because that's an attribute, I hope you can guess what will happen if I change it. It just changes the width of the bar. Now they're super wide. That's all it does. It's an attribute, so it applies to all of them universally. Okay. So that's all real important for understanding actually how this thing works. Does that make sense to everybody? You can pass anything you want into this. Any function that creates numbers, you can pass in through a StatSummary command. The only reason that we use mean underscore SDL from ggplot instead of smean.sdl is because it reformats those 3 columns to the names we need, xmin, ymin, ymax, and y. You could alternatively call this and do it yourself. Same thing. Doesn't matter. This just skips a step. That's the advantage of using that function. Okay, so that's the stats layer. Coordinates layer. Key to understanding why there's a coordinates layer is to understand that the scale commands, the aesthetics, actually define where you're looking, what the data contain. The coordinates layer is like, all right, my graph's done. Now I'm going to take a camera and move it around somewhere on the graph. That's what a coordinates layer does. It says where on the graph are we looking, or where in the figure are we looking, not what does the figure contain. So you're usually going to use chord Cartesian. We don't make pie charts in psych, really, or education, etc. We mostly focus on histograms, frequency polygons, scatter plots, that kind of thing. So you're probably not going to need anything in the polar coordinate system. You're probably not going to need anything in any other coordinate system, to be honest. Cartesian plane is pretty much all we ever use. This is, however, where we typically will specify our viewing limits. This is the most useful thing to do with chord Cartesian, because you can specify x lim and y lim, which basically just says, I only want to look at x values between 1 and 2. That's different, again, from scale underscore x underscore continuous parentheses limits equals 1, 2, because that says only include data between 1 and 2. Those are different. So the scale command would say, the scale version of this would say only look at data between 1 and 2. The chord Cartesian version of this says, or only include data. I split it up. The scale version would say only include data between 1 and 2. The chord Cartesian version says only look at data between 1 and 2. So those are very different. You specify limits for the axes. Data science default ideology is to display data with as much detail as possible. That is an explicit bad practice in social science. Very explicitly, we are often told, for example, if you have a 5-point Likert scale, then the anchors of your y-axis should be 1 and 5. Do not hide what your axes are in order to look more impressive. By default, GG will do whatever looks most impressive. So you may need to respecify your limits wider in order to get the full view of a variable. If, for example, you have a heavy skew, like say, for example, you had a 5-point Likert type scale with a mean of around 4 point something, and you had a heavy negative skew, and you had no values between 1 and 2, well, by default, ggplot would just not show you anything below 2. So you would need to respecify that here. You can sort of accomplish the same thing with chord equal, but you have to use more attributes. Cartesian is just a little easier. And that's almost really all you need to worry about in terms of the coordinates layer. The facets layer is really about duplicating your screen, duplicating your figure in terms of multiple views, which are called panels. So if you need to do two panels side by side, say for example you're doing a 3-way ANOVA or a multi-way ANOVA that's more than 2, whatever it might be, then you might want to have additional panels beyond, so that once you split it up, actually 4-way I guess, no. Once you split it up by 2 axes and given it 2 different colors, you might need to replicate it again with a new panel. That's the major situation where this occurs for us. So the way that you do this is using formula notation. Formula notation is something that you will get real familiar with next week. Formula notation, right here, for example, says specify a univariate linear model of y with 2 variables, 2 predictors, x1 and x2. This other one right here says take a model, a univariate linear model of y, and take all other variables in the data frame as predictors. What's that? That's what that period means, like regular expressions, right? So it's take all other data that you can find. So this notation you're going to get real familiar with very soon. But right now, all it's used for in the facets is to specify rows and columns of panels. It's in the same order as data frames and matrices, rows, then columns. That's the easy way to remember it. So if you specify a variable here, tilde dot, then that will create multiple rows based on that variable. If you use it dot tilde, that will create multiple columns based on that variable. If you do variable tilde variable, you end up with both of those splits. And if you need more than that, you should really simplify what you're trying to visualize. And you can, there's actually ways to do that where you can have multiple panels, but you probably need to refactor at that point. So, for example, this is a ggplot of my data frame with aesthetics on the x-axis condition, y-axis score, and create columns specified by gender. Note that you do not need to put this inside your aesthetic unless you need it for your aesthetic for some reason. If, for example, you wanted your entire left panel to be green and your entire right panel to be blue, then you could put it in the aesthetic here, but it's just superfluous. You don't really need it because it's already split apart. Okay. That's it for facets. Themes. Themes is where you will spend a lot of time when you're trying to make publication quality graphs. When you're trying to get things exactly where they need to be, and all the colors right, and all the specifications right, you will do a lot with themes. Themes are basically entirely what we think of as aesthetics, as in the window dressing of a figure. So this is about making font sizes different, specific colors of text different. It's about controlling specific pieces of information and how they're presented. Font. Changing format of piece is usually done with these four elements: element text, element line, element rect, and element blank. Element blank is the one you'll probably use the most because what it does is it says, I don't want this. So if you have an axis and you're like, I don't want to show that axis, then you would probably assign it to an element blank in order to get rid of it. This is a cheat sheet essentially of all of the base components in the themes layer that you might want to modify. There are more than that, but these are the ones you most often need. In terms of element underscore text, you have plot titles, legend titles, axis titles, strip, which refers to the little piece of text above panels. You have element underscore line, which is ticks, lines, panel grids. And you have element underscore rect, which is these guys right here, the backgrounds and the borders. If we go back into R and type question mark theme, you will get a full list of all of the things you can do with themes, helpfully labeled out, helpfully laid out in a giant list, along with the kind of things that it wants. So say, for example, you're like, you know what, I need to modify something about a panel, but I don't remember what panels do. Then you can just find in this list, oh, here's all the stuff I can do with panels: backgrounds, borders, spacing, grids. And then you can look here and say, well, what does it take? Aha, this is an element line if I want to modify panel.grid. So if you want to do that, if you want to modify some specific element, you're not quite sure how to do it, use the help theme in order to figure out what those specific pieces are. Okay. Margins, spacing, and positioning. I mentioned these already a little bit in terms of how you position, for example, legends. But one of the things that you will notice is sometimes just numbers are being used for positioning, and you're like, where did that number come from? The answer is it's a unit. And what a unit is, by default, is one axis length. So if you were to define the position as 0.9, as a vector, for example, then that would mean 90% of the way up x and 90% of the way up y. That's all that means. So you can also position them with presets. If you look back in the file that I was just showing you, for example, and we go to legend.position, you will see all of the presets of legend that are possible. So if there are presets, you will see them located in this file. So make heavy use of this. It does depend visually on your coordinates layer. ggplot unit is defined as one axis length from origin. and can be arbitrarily created or converted. I think you had an exercise in data camp that you did this like for centimeters, so that you had one thing in centimeters and one thing in meters or something like that. We don't deal with that a whole lot in the social science perspective, so usually you'll just do it in percentages. One warning though, this units aspect is still dependent on RStudio. RStudio creates when it creates that initial plot down here, that plot right there becomes the length of the axis. So for example, if I were to define something as being at 90%, right now, it's 90% of a square. If I do it at 90% now, it's 90% of a rectangle, which can actually make where it appears slightly different. So this is something you just have to fiddle with. And when you're ready, when you're done with it exactly where you want it, then you export it immediately. And it will just scale up whatever it looks like in RStudio. If you do that in the wrong order, like if you assume, oh, I've specified 90% and 90% is always in the same place, it probably is not. Actually, let me see if we have time for one of these. Let's go up here. So we did a bar plot on empty cars just a second ago. Uh-oh, I confused it. Okay, let's go all the way back up to the top. There we go. So there is that. I'm going to look real carefully for some legend options in terms of what we can put here. So we're using cell. So let's try color equals VS. Anybody sees what I'm doing? Oh, there we go. Good enough. So this has created a legend over here. And if I go plus theme legend.position equals bottom, for example, that should be nice and easy. Positions are at the bottom. But if I do C.9, what will that do? Now it's up here. Notice it's specifically where it is. It ends at the right side of this guy, and it's kind of halfway between this one. What happens, though, if I do this, now it is very different. Okay? So when you position in absolute terms, it's based on its physical location in that window. So that means that based on... You generally want to avoid absolute positioning unless you're literally about to export the figure to a PDF for inclusion in a paper. Otherwise, don't spend time fiddling with positioning like this because it'll drive you crazy because it'll change. So use the presets for the positions like bottom, left, right, etc. And if you use absolute positioning, last step, like literally the very last thing you do, or it will drive you a little nuts. Okay. The reason that happens is because R uses what's called vector graphics and not what are called raster graphics. What a vector graphic is that a graphic is designed in terms of the polygons it contains. So this picture, as a vector graphic, for example, says this is a rounded polygon, this is an oval, this is a triangle, etc. So that way when you scale it up or scale it down, it always looks the same. That's the advantage of vector graphics. Computers, though, use what are called raster graphics, which means that every dot you see here is a separate variable that your video card is pushing to this screen, or this projector is specifically. So there's a little white dot here, and 60 times a second it's saying, make that dot white. You can also save a picture that way. That's called a raster image. But the problem is, if this is a raster image and you enlarge it, none of these other little pieces of information are in that picture. So when you enlarge it, it becomes blurry. So the way that I created this actually is I got a vector image right here from this website. Took this vector image, shrunk it down, re-enlarged it, looks the same because it's vector imagery. Then I rasterized it to convert it into dots and enlarged it, and it turned blurry. So R uses vectors. So that means that that line won't get blurry no matter how gigantic you make it. You can make a wall-sized poster of your figure and it would look exactly the same because it's using vector graphics. But because it's using vector graphics, when you change the shape of the graph, it fundamentally changes the location of objects because now it's like, I'm not sure what 90% means given what you told me. So that's why this happens. There's a little background on graphics theory, so that's why that's happening. Quick plots is a thing that you saw a little bit using qplot. Don't use qplot. Qplot is actually a shortcut for people that already know base R graphics. So then if you already know base R and you're already making plots using plot, bar plot, hist, etc., then it's really easy to switch over to qplot using the same syntax. But since you never really learned base R graphics, just don't do it. It's a waste of time. So don't deal with quick plots. But what you do want is this guy, GG pairs, which comes from the ggalley library, and be very careful of the capitalization there. If I do library ggalley, I can do GG pairs G of MT cars. And what that's going to do is run a whole crap ton of graphs. These are all plots that it's making right now. And it's going to give me a really amazing summary graph, which is right coming up here. What this immediately gives me is correlations between all variables, histograms of every variable in the data set, and scatter plots of every pair of variables, automatically in one command, using the ggplot system. This should be the first thing you do in every data analysis you ever do. This should be the first thing, like immediately, is anything normal? Do we have any weird-looking relationships? Is there strange curvilinearities I need to look out for? All of that should be done using this command first, every single time. So anytime you're working with your own data set, again, two commands, library ggalley with two capital G's, and GG pairs is the actual command. You might have seen that, and I think I wrote it down. Yeah, you might have seen that as the command plot matrix. Plot matrix used to be in ggplot too, but they took it out. So don't use plot matrix, use this instead. But GG pairs is an enormously valuable data visualization tool. Beyond about this many variables, it starts to get hard to see. So if you do want to do that, then you might do, for example, specific variable subsets the same way that we normally would. You might instead pipe into GG pairs a select statement. You could do like select all variables that start with Q and then do that. Whatever you want to do, it'll all work. But around 10 variables at a time, you can get a really good visualization of this. And I would strongly recommend it. And you'll need it for the project.